Well, Kepler has provided us a description of how the planets move. Newton provides us a reason that the planets move. Have you ever thought about why the Earth stays in orbit around the Sun? It's moving fairly fast. It's a large object. Why doesn't it just fly off into the space between the stars? Why is the path an ellipse? Well, Newton was able to answer those questions, and we're going to have a measure of understanding of Newton's laws and Newton's understanding of gravity as we go through this video. So first, some terminology. When we talk about an object's velocity, we need to know the object's speed, and in the metric system, meters per second. A basketball player is about 2 meters tall. So a meter is about 3 feet. But the speed in meters per second, and velocity also has direction. That is important. Velocity is speed and direction. Another term for motion that's important is acceleration. And acceleration measures the rate at which the velocity is changing. And the units of acceleration are meters per second squared. I've written it here as meters per second per second. So if the acceleration is 3 meters per second squared, the meaning of that is the velocity is changing by 3 meters per second every second. And again, the acceleration, in particular circumstances, you'll have to tell the direction of the acceleration. Then force. Force is a push or pull, and force creates acceleration. So the acceleration, the speed of the object may change, or the acceleration may just change the direction, or both may change. So force causes acceleration. Acceleration causes a change in velocity. I should keep that sequence in mind. Force causes acceleration. Acceleration causes a change in velocity. Now, Newton's first law, there are 3 laws of his motions. So Newton's first law of motion, if we take a look at all the forces that act on an object, if we add them up and they add to 0, then the speed and direction of the motion are constant. The velocity will be constant. So if we're in a situation where there's a force of 6 newtons to the north, and Newton is the metric unit of force, 6 newtons to the north, and 6 newtons of force to the south, those two forces will add to 0. And whatever the object is doing, if it's at rest, it'll stay at rest. If it was moving towards the east at 7 meters per second, doesn't matter what the number is, that velocity will be constant. The speed and the direction will stay constant. So it's really nothing interesting happening here. If the forces add up to 0, if they're all balanced, then the velocity is constant. The object keeps on doing what it was doing before you started looking at it. Inertia is the measurement, or the quantity that tells us how difficult it is to change the velocity. And that's changing either the speed or the direction. An object has more inertia if it's more difficult to change its speed or change its velocity direction. We measure inertia with mass, and we use kilograms in the metric system. So mass measures the amount of inertia. If something has a mass of 90 kilograms, then it's more difficult to change its velocity than for an object that has 20 kilograms. So the more mass, the more difficult it is to accelerate the object. This can be combined in understanding to Newton's second law. And in this law, force is equal to mass times acceleration. Force is equal to mass times acceleration. Force is equal to mass times acceleration. So if we have 1 Newton of force, then a 1 kilogram object can be accelerated at 1 meter per second squared. Let's make the numbers not all 1. Of course, 1 equals 1 times 1. But let's suppose that we have 10 newtons of force. 10 newtons of force, and it's a 2 kilogram object. 10 newtons of force and a 2 kilogram object. We divide both sides by 2. 10 over 2 is 5. The acceleration would be 5 meters per second squared. If the force is 10 newtons, the mass is 2 kilograms, the acceleration would be 5. If the mass was 5 kilograms with the same force of 10 newtons, 10 newtons of force, 5 kilograms of mass, the acceleration would only be 2 meters per second squared. As the mass increases, the acceleration decreases for a fixed amount of force. If the mass increases, the acceleration decreases for a fixed amount of force. I probably should mention also the force and the acceleration, both of those have directions, and the acceleration is always in the same direction as the force. Newton's third law, all forces come in pairs. So you could lean against a wall and push on it. The wall will push back on you. If you push on a wall, the wall pushes back on you. This is automatic. That's the way the universe works. Sometimes this is called action and reaction, but that's a little bit misleading. There is no delay for the reaction type force. If you push on the wall, there's no delay for when the wall starts pushing back on you. So Newton's third law. These forces come in pairs. There is no single force in the universe. And the forces of Newton's third law always act on different objects. They act on different objects. When you're standing on the floor, your feet are pressing down on the floor with a force equal to your weight. The floor pushes back up on you. So you push on the floor pushes on you. The forces are acting on different objects, you and the floor being different objects. So Newton, let's go into his background just a little bit. Had a country estate and had apple orchards in that country estate. As we talk now about gravity, move into the concept of gravity, Newton probably was not hit on the head by an apple, but he most certainly would have seen apples fall off the tree in his apple orchard. So we could ponder that just a little bit. And if the Earth's gravity can cause an apple to fall towards the Earth, can the Earth's gravity cause the moon to fall towards the Earth? Well, that's really kind of a trick question. The answer is yes. The Earth's gravity is pulling the moon towards the Earth, but the moon has a sideways motion that keeps it in orbit, and it misses the Earth. It doesn't fall directly towards the Earth. The moon is moving forward in its orbit, and as it is pulled towards the Earth, it moves sideways at the same time and completes an orbit. But Newton said the Earth's gravity extends out into space. The gravity is a long-range force. You don't have to be right at the surface of the Earth to experience the pull of Earth's gravity. Newton said the Earth's gravity extends on out to the moon. And he was able to use some astronomy observations, the size of the moon's orbit, and the amount of time for the moon to complete an orbit. That helped Newton confirm his model for the law of gravity, on how we could calculate gravity. And here it is. So Newton's universal law of gravity looks a little scary, but it's not that bad. Capital G is a constant called the universal constant of gravitation. And I should mention, for my class, we will not calculate this in detail. We will discuss what happens to the force if you double the mass, what happens to the force if you make the distance 3 times greater, questions like that. But we will not go factor by factor here and calculate the force. So universal constant of gravitation, it takes 2 masses to have the force of gravity. Mass 1 and mass 2 attracting each other. We put them in kilograms if we were doing the calculation. And then the distance squared between the centers of the 2 objects. And we would use meters if we were going to do this calculation. But as I say, in my class, we will not do the detailed calculation. So this is Newton's universal law of gravitation. Universal because the force of gravity extends throughout the universe. Right now, Jupiter is pulling on you. You are pulling on the planet Venus. If you put in the 2 masses, Venus mass and your mass, and the distance squared, you could calculate. So universal, every piece of matter attracts every other piece of matter in the universe. Newton's universal law of gravitation. And very important for the study of orbits, Newton was able to use this law, and with the aid of the calculus, the mathematic technique called calculus, You're able to prove that with this force law, the orbits are ellipses. So this explains why the planets move on ellipses. They move on ellipses because of the nature of the law of gravity. The way the force of gravity operates, we get this behavior. The r squared here is somewhat interesting. We can calculate the force of gravity on the Earth. It causes a certain acceleration of an apple as it falls towards the Earth. From the knowledge of the moon's orbit size and the period for the moon to go around the Earth, we can calculate the acceleration acting on the moon. And it turns out that that acceleration is about a factor of 3,600 smaller than the acceleration at the surface of the Earth. And both of those acceleration due to gravity, 3,600 smaller. The distance from the Earth to the moon is about 60 Earth radii. 60 Earth radii. So if you put in, when we're doing this experiment on the surface of the Earth, we put in 1 for the r value, the radius of the Earth, and we get a certain force, we get a certain acceleration. When we take a look at the moon, we put in 60 for the r value, we square that, and we get 3,600, and that's the factor how much smaller the acceleration will be. So this study of the moon's orbit, astronomy, provided confirmation to Newton that he had it right here, that the denominator here is the square of the distance between the centers of the two objects. So let's take an example of this. What will happen to the force if mass 1 doubles? If we consider a planet, if the size stays the same and somehow we can double the mass, let's say, of the Earth, with the size staying the same, what would happen to the force? Well, if m1 is twice as large, everything else being constant, the force will be twice as large. What happens to the force if r doubles? We become an astronaut, and instead of being on the surface of the Earth, we go out to an altitude of equal to the radius of the Earth, that above the Earth. So if you would make your own sketch of this, the astronaut is now 2 radii of the Earth away from the center of the Earth. We're going to double the radius. At first, the astronaut was on the surface of the Earth. Now the astronaut will be 2 times the radius of the Earth away from the center of the Earth. Well, if there's a factor of 2 in here, the square applies to that 2, and we get a factor of 4 mathematically. The force will be 4 times smaller. If we double r, that factor of doubling gets squared, we get 4 in the denominator, a factor of 4 r squared, and the force will be 4 times smaller. If the r increases by a factor of 3, if the astronaut is now 3 times the radius of the Earth, away from the center of the Earth, 3r, that square would apply to the 3r, and we get a factor of 9. 3 squared is 9. The force would be 9 times smaller. If the astronaut goes out to a distance of 4r away from the center of the Earth, 4 squared is 16. The force becomes 16 times smaller. If r becomes 5r, 5 squared is 25. The force becomes 25 times smaller. But it doesn't go to 0. It just keeps getting smaller and smaller as r increases. So as r increases, the force decreases. Objects have less gravitational force if they're further apart. What if we would make the radius half, this distance between centers, make it half as big as it used to be, a factor of 2 smaller? Well, if r is smaller, r squared will be smaller, and the force will be larger. And it works in the same way, you just have to change your wording of the result a little bit. If r is a factor of 2 smaller, that factor of 2 squared is a factor of 1/4 now in the denominator. Don't worry about that. Take the principle, if r is smaller, the force is larger. If r is twice as small, remember the square, and the 2 squared becomes a factor of 4, the force is 4 times larger. If r is decreased by a factor of 3, the objects are much closer, just 1/3 r in between their centers, that factor of 3 gets squared as a factor of 9, and we get a force that's 9 times larger. If r is 4 times smaller, the force will be 16 times larger. If r is 5 times smaller, the force will be 25 times larger. Think to yourself, what if r is 10 times smaller? We go to 1/10 r for the separation of the objects between their centers. 1/10 r. You should square that factor of 10. That makes a factor of 100. The force would be 100 times larger. So there's our principle. If the mass is bigger, the force is bigger in proportion. For the radius, if the radius, the distance between the centers, if that gets bigger, the force gets smaller. So it's inversely proportional to the square of the factor of the radius. If r is 6 times larger, the force is going to be 36 times smaller. 6 times larger, the objects are further apart. If the radius becomes 1/6, what would the new force be? Well, that 6 again squared is 36, but now we're closer, so the force goes up by a factor of 36. That's Newton's law of gravity, and it can be used to explain Kepler's laws. So I ask you to keep reading, write down some questions, and ask those questions.